Welcome back, everyone. In this lecture, we're going to go over the solutions for the convolutional neural network exercise questions. Let's head to the notebook and get started. Okay, here we are at the exercise notebook. First thing we want to do is actually load up the data set. We can do this simply by running the cell from the exercise, so TensorFlow keras datasets, fashion mnist, and next we want to use matplotlib to visualize the data. That means we actually need to import matplotlib.pyplot as plt. And then if we take a look at the training data right now, if we take a look at the shape of it, it's 60,000 images, 28 by 28. So let's go ahead and just grab one of those images. So now we have a single image there, and then to display it, just a single image, we can say plt imshow, and that should display the image. And in this case, since the very first image item is an actual boot. Okay, so we've done that. We understand that we have this data. Now it's time to process the data. Luckily for us, we can confirm that the maximum value is 255 by just saying .max, which means I can then do a simple pre-processing by saying xtrain is equal to xtrain divided by 255, and that xtest is equal to xtest divided by 255. After that, we can reshape the x arrays to include that fourth dimension. So what we can do here is we can say xtrain is equal to xtrain reshape 60,000 28 by 28 by 1 to make sure we include that color channel, or a singular color channel I should say. And then xtest is going to be xtest reshape, and in this case it's 10,000 points. So that's 28 by 28 by 1 color channel. So we've reshaped it to include that color channel, and then we also want to make sure we convert the labels to be categorical. So we can say from tensorflow.keras.utils import to categorical, run that, and then we'll say ycat train is equal to this call of to categorical, and we can say ytrain. It should be able to infer that there's 10 classes, but we can always make sure of that by passing it in as well. And then we'll say ycat test is equal to categorical on ytest. And hopefully this feels pretty familiar, given that we've already done almost this exact same process on the mnist dataset. After that, it comes time to build out the model. So we want to use TensorFlow and keras to build out this sequential model. So let's start with the imports. We'll say from tensorflow.keras import sequential, and also from tensorflow.keras.layers import, and we're going to use dense, convolutional 2D, as well as a max pooling layer. That's another 2D there. And then we also need to flatten out the results later on in our model. So we have that ready to go. We can create our model, and then let's add in a convolutional layer. So that's convolutional 2D. We'll go ahead and set filters equal to 32. This is a value you can play around with, but we'll set the defaults that we essentially did last time. So 4x4 kernel, and then we need to specify the input shape to be 28 by 28 by 1. And we can also play around with the activation function. So I can say activation is equal to rectified linear unit. Once we've done that, we'll go ahead and add in a pooling layer. So that's max pool 2D, where the pool size, the default is 2 by 2. So I could just leave it by the default or specify it myself, but we'll go ahead and just keep it 2D by 2D. Okay, next after that, we'll say model add, and we'll flatten it out. You can add in more convolutional layers if you want, but for our use case, that should be enough. And then we'll add in a dense layer call with an activation of a rectified linear unit. Last layer should be a dense layer that has the same number of neurons as number of classes, so that's 10 neurons. And we also have to make sure that it's softmax because it's a multi-class classification problem. And then after that, we will compile this model. If you want, you can go ahead and add in things during training like an early stopping mechanism, but for right now, we'll just keep things simple. We'll say categorical cross entropy. We'll go ahead and just choose an atom optimizer, see how that works. And then let's go ahead and keep track of accuracy as well. So we'll say accuracy is one of our metrics. We compile this, we can confirm this through a model summary call by saying model.summary, and there we can see the results. Okay, then it comes time to train the model. The amount of epochs is really up to you. We left some results here so you can see that essentially after a couple of epochs, the performance tends to hit 0.95, even after just like 3 epochs. So we'll go ahead and just train for, let's say, 3 epochs here. So model fit on X train, Y cat train, and as an option, you can also pass in validation data. Let's go ahead and do that. We'll say validation data is X test with Y cat test. This wasn't required by the exercise, but you can go ahead and play around with that. And let's say epochs is equal to 3. So we won't train it that much. We should get pretty good results even out 3 epochs. And upon running it, you should start seeing it train. For the sake of this video, I'm only doing 3 epochs. You can always add in early stopping and see how it performs. We can see here, we're starting to reach 90%, so that's pretty good accuracy. And on one more, hopefully we reach 90%. Perfect. If we train for a couple more epochs, it's very likely that we would have hit 95%. Okay, evaluating the model. So lots of different ways we can do this. We'll go ahead and just follow the same couple of metrics we did. Let's just ask what the model metrics were. So we can do this by saying model metrics names. Here we can see loss and accuracy as the results. There's lots of different options we can do. I can say model history.history, turn that into a data frame, and then say something like metrics is equal to that. And whoops, make sure we import pandas in order to do this. Import pandas as PD. There we go. And then I should be able to plot out my metrics. So nothing too crazy here. Whoops, we've got to make sure we plot relevant metrics against each other. So let's plot in loss versus validation loss. Plot that out. It looks like they were still both going down. We probably could have trained for more than 3 epochs, but for the sake of this recording, didn't want to waste time just training. And then the other one we could do is accuracy versus validation accuracy. And hopefully they're both also continuing to go up. And there we go. So clearly we could have been training for more epochs, but let's go ahead and see how we did overall. We'll say from sklearn metrics, import a classification report. And then what we can do here is say predictions is equal to model, predict classes, and we'll do that on our X test set. And then we simply print out our classification report comparing Y true, or really Y test, to our predictions. Okay, so based off the fact that we probably didn't train for enough epochs compared to the 10 epochs in the solution, we're still actually performing pretty well. We have 90% accuracy, which is essentially what we were aiming for. Lots of other things you can do here, like experiment with convolutional layers, adding in more neurons, etc., playing around with kernel sizes. But hopefully, this was a good exercise in just you following the general workflow for setting up a convolutional neural network. Okay, that's it for this section. Thanks, and I'll see you at the next one.